Okay, so today we're going to be working on the last part of chapter 3. Again, Cramer's rule, volume material, what you can do with some of these stuffs through the determinant. Again, chapter 3 is all about what can we do with the determinant. And so I'm going to finish up that material. I think we ended up on Cramer's rule last time, and so we'll kind of reinforce that concept as we move on. And then again, I'm going to be moving on into chapter 4 by the end. And on next Tuesday, we'll be continuing going into chapter 4. But on that Thursday, I plan on having a big day of review for your next test. And then the following day will be the test. And then we'll pick up right where we left off. Probably on that Tuesday, when we review, I'll review a little bit. And then maybe the last 15, 20 minutes, just keep on talking about chapter 4 material. But it does link together with all the stuff from chapter 2 and chapter 3. So here we go. Again, last time we were talking about Cramer's rule, and I had all these wonderful, bizarre formulas for you guys about Cramer's rule. Cramer's rule is a way of solving for x on a system of equations. But we've been doing that since chapter 1. So with that being said, the idea is actually using this determinant. And I'll have to admit to you, this is a small scale solving. It is not efficient to be able to do the Cramer's rule on large matrices. So the most you'll ever do a Cramer's rule on is a 3x3 matrix, because after a while, taking the determinant gets rather painful to be able to calculate 4x4, 5x5, 6x6 without doing the reduced echelon form. If you're going to be doing it that way anyway, you might as well just go and solve for x the traditional way. So this is a very specialized formula, but it's absolutely brilliant. And just to remind you, you've got a system of equations, and you can write it as a matrix, AX equals B. And then we talk about these submatrices, AI of B. And AI of B is the matrix that is set up by, basically it's matrix A, but at the ith column, you replace the ith column with B. So you have an A1, an A2, an A3, an A4, dot, 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 an AN. So you get one for every column that you get, but each column where you subscript it, that's what you replace the column vector with the B vector, what the equation is actually equal to. And then, from that rule, you end up getting this, that you're going to solve for so many variables, an x1, x2, x3, or whatever. And so, and again, 3x3 is the most you'll ever want to use with this stuff. So x1 would be equal to the determinant of a1b, so you replace the first column of A with the B, take the determinant of that guy, divided by the determinant of the coefficient matrix, and that'll give you the solution for x1. x2 would be you replace the B with the second column, take the determinant of that matrix, divided by the determinant of A, the original coefficient matrix. That'll give you the solution for x2, and x3 would be the same thing if it went up to a 3x3. You take the third column of A, replace it with the B vector, and then take the determinant of that and divide by the determinant of the original coefficient matrix. That'll give you x3, and you got your answers. But to be able to use Cramer's rule, the one big deal is the determinant of A can't be 0. A has to be invertible, non-singular, and so because you can't divide by 0, so this is a more efficient way than actually finding the inverse and multiplying by both sides by it, or taking A, augment it with B like we did in chapter 1, and row reducing it and getting the solutions that way. And when A is invertible, you get a unique solution. This x1, x2, x3 is giving you the unique solutions on these guys. So again, just kind of highlighting what we did last time. So this is what we started with. I'm just trying to refresh your memory. And we did this example just to kind of highlight it again, because I've got more examples coming down the road for you guys. So use Cramer's rules to solve this equation. This is what we did last time. 4x1 plus x2 equals 6, and 5x1 plus 2x2 equals 7. So I wrote it as a matrix. 4, 1, 5, 2 times the vector x1, x2 is equal to, there's your B vector, 6, 7. And so for x1, you take the 6, 7, replace the first column with it, so it's 6, 7, 1, 2. And then it would be divided by the original determinant of the A matrix. A was the original coefficient matrix, 4, 1, 5, 2. And we end up getting 5/3 for x1 when we took the determinant of the numerator or the determinant of the denominator. And for x2, we replaced the second column on the A matrix with 6, 7. And then we took the determinant of that, divided by the determinant of the A matrix, and we got -2, 3, and that gave us the solutions. So it's a very nice and actually quite ingenious formula to be able to calculate the solution using determinants for this stuff and not doing the reduced echelon form type thing here. Okay? So, again, that's what we picked up last time. So how can we make these a little more interesting? All right. Again, last time, well, let's just do this one right here. All right. Just good practice here. Solve this guy. Again, good practice to set up what I'm about to set up for you guys. So I want you to use Cramer's rules to solve this equation. 3x plus 2y equals 7, negative x plus 3y equals negative 2. Again, you will notice that the most I'll ever give you is either 2 equations, 2 unknowns, or 3 equations, 3 unknowns. After that, Cramer's rule is no longer efficient for us to be able to use it to solve. So, first thing I'm going to do is what? Again, let's prepare like it's going to be your test, which is coming soon. What would you do first? Outstanding. Write it in matrix form. So writing it in a matrix form, we get this. 3, 2, negative 1, 3, multiplied times your x, y, that's your unknown vector there, is equal to 7, negative 2. And it's now the form of matrix A times vector x, which is what we're trying to solve for, equals vector B. Now, from that, we write up Cramer's rule on how to figure out your variables. There are 2 variables, x and y. So how do I solve for x? X would be equal to, and it's the determinant over determinant, and the denominator determinant is the coefficient matrix. 3, 2, negative 1, 3. Okay? And what about the numerator matrix? What you do, because this is x, or the first variable, you're going to replace the first column with the B column. So that would be 7, negative 2, that goes in the position of the first column of the A matrix, and the second column of the A matrix is just the A matrix, the rest of the A matrix there. Okay? And then, just because we're looking for a pattern here, how do I get the other coordinate, the y coordinate? You divide by the A matrix again, which is the original coefficient matrix, 3, 2, negative 1, 3. And again, what makes it efficient is you've already calculated it already, so calculating it again shouldn't be that difficult. And then the y, well, y is your second variable, so you take the second column of A and replace it with 6, 7. So the second column, the 2, 3, gets replaced with the 7, negative 2, that is. And then the first column would stay the same, 3, negative 1. And now it's 2 by 2, so let's go solve this thing. So to take the determinant of 2 by 2, you do the main diagonal, 7 times 3 minus the off diagonal, 2 times negative 2, divided by main diagonal, 3 times 3 minus 2 times negative 1. So 7 times 3 is 21, minus 2 times a negative 2, negative 2 times negative 2 is a plus 4, over 3 times 3 is 9, negative 2 times a negative 1 is a plus 2, and I end up getting 25 over 11. For the second variable, I do the main diagonal of the numerator. That'll be 3 times negative 2 minus 7 times negative 1 divided by, you've already done the determinant of this guy. What do we get? 11. Again, that's that efficiency aspect. You've already done it. You can just plug it in. So I end up getting negative 6, negative 7 times, 3 times negative 2 is negative 6. Negative 7 times a negative 1 is a plus 7 over 11. So I end up getting pretty much 1 over 11. So the answer here is x is equal to 25 elevenths, y is equal to 1 11th. And if you want to write this as a vectored value, because we're trying to solve for the vector x, y, that would now become the vector 25 elevenths over 1 11th. And again, it is efficient, it is quick. Again, 2 by 2, at most 3 by 3, but after that, it takes too long to be able to calculate the determinants of these guys. So again, we're looking at from a computer science perspective in terms of efficiency, because you should be, as computer science majors, thinking about how to program this into a computer to get the computer to map out what the analytics we were actually doing on these problems. So how can we make these more interesting? Oh, this one. And again, I think you got one on your homework like this, your traditional homework, as well as your MyLab online homework that we got. So here's the deal. Solve using Cramer's rule. And then for which S is the solution unique? So now I'm going to start talking theory questions at you. Basically, I threw this arbitrary S variable in this thing, and you got to tell me something about S to make sure the answers are unique. That's really the crux of the question here. So, solving this thing using Cramer's rule so we can figure out which S will actually make the solution unique. So, I've got 6S times x1 plus 4x2 equals 5. I got 9x1 plus 2s times x2 equals -2. Okay? So, if I'm going to solve this thing using Cramer's rule, again, I'm going to write it as a matrix equation. So, this would be 6s space 4, 9, 2s times my vector, my variable, x1, x2 as a vector, and it's equal to 5, -2 as a vector. So it's now the form ax equals b. Right? So, here we go. What would x1 be equal to? Well, it is a quotient of determinant over determinant. The denominator terminant is always the 6s, 4, 9, 2s, the determinant of the actual coefficient of matrix A, the coefficient matrix, matrix A. But for the numerator, we end up getting this. Because we're solving for x1, you replace the first column with the b column, 5, -2, but the second column of A would stay the same, 4, 2s. And let's go ahead and get that solution here. So main diagonal minus off diagonal. And now you discover very quickly that with something that if you've taken differential equations, you've figured out very quickly. The problem in the world is this, especially for math people, and that is the idea of us using the letter S used to kill me in differential equations because my S's look like 5s, okay? And if I'm not paying attention to it, I will blow up a problem like nobody's business, okay? So you learn this. And it took me until I got into differential equations and my linear algebra class to understand that math people actually have to be neat. Kind of sad, and it kind of scares most of us, but we have to be neat because it's real easy for us to make a careless error because of our sloppy handwriting. So at this point, I went from calculus where I just kind of chicken scratched everything to actually being very organized and methodical in terms of what I write down. I know it's hard to tell here because that really does look like a 5, but I know it's an S. So here we go. 5 times 2s would be 10s minus 4 times -2, and 4 times -2 is -8. And my denominator, look what I get here. I get 6s times a 2s, and that's what, 12s squared, minus a 4 times a 9, which is 36. So again, cleaning this up, I end up getting 10s plus 8 divided by 12s squared minus 36. And then the solution for x2 would be, again, for x2 is your second variable, or it's the second column is what we're going to replace the b with. So I get the matrix that we're going to take determinant of 6s, 9 for the first column, and for the second column, replace the 4, 2s with 5, -2. And divided by the original coefficient matrix, 6s, 9, 4, 2s. And so now, 6s times a negative 2 is a negative 12s. Minus 5 times 9 is what? 45? Okay. Over, now I've already done this guy, just in case you wanted to know. It is 12s squared minus 36. So I end up getting negative 12s minus 45 divided by 12s squared minus 36. Now, let's talk about cleaning up these answers, and then I'm going to go answer the question. Look at that numerator of x1. I got 10s plus 8. What can you factor out of that, guy? You can factor out the 2. And you're left with a 5s plus 4. What can you factor out of the 12s squared? You can factor out 12, okay? Minus 36. You can factor out 12. And you're left with s squared minus what? 3. Does that make sense? But this is linear algebra, which means we've done a lot of algebra just to get to this class. I believe you can factor that s squared minus 3. Factor it, please. So you end up getting 2 times 5s plus 4 divided by 12 times, how does s squared minus 3 factor? It is a difference of squares, but you got to look in the right way. What you got? S plus the square root of 3 times s minus the square root of 3. That's right. We're going all the way down to rationals on this thing. What about the, so that is my answer for x1, and I will go ahead and circle it. Completely in factored form. And the reason why I want it factored form is for the second part of my question I'm going to have here. How does x2 going to factor? Well, what can you factor out of that minus 12s minus 45? Question. You can, if you wanted to knock it down like that, but at this point, it's not going to matter in terms of what I'm after the next one. So I would have accepted it either way, but sure, clean it up the best you can. What about this guy? What can you factor out of this guy here? You can factor out a 3. When I factor out a 3, what am I left with? Let's take out a negative 3. It's a lot better. Okay, so what am I left with? We can factor a negative 3 out of a 12s, you're left with a 4s. You factor a negative 3 out of a 45, you're left with a plus 15. Divided by, you can factor the 12 out, and you're left with s squared minus 3. And again, doing the same thing. This would give you negative 3 times 4s plus 15 divided by 12 times s plus square root of 3 times s minus the square root of 3. And since you're talking about it, you know that 3 will go into the 12 4 times, right? So what I end up getting here is this. x1, when you reduce it down, you're going to get 5s plus 4 divided by 6 times s plus the square root of 3 times s minus the square root of 3. And you're going to get x2 to be equal to a negative parentheses 4s plus 15 divided by a 4 times s plus the square root of 3 times s minus the square root of 3. Does that make sense? But there is a part B to this question, and that is this. And for which s is the solution unique? So this is my answers. But when do I get to have solution unique? What's the deal? S cannot be equal to what numbers? What is it? Negative the square root of 3, and s cannot be equal to positive square root of 3. As long as that is the case, you will get a unique solution for x1 and x2 every time. And the real reason is the square root of 3 and negative square root of 3 is what actually makes my denominator equal to 0, which obviously is a violation of classic math laws. Does that make sense? So I always get a unique solution, and it will also, with these variables, it will identify the places that I have quote-unquote problem points at. Won't be able to solve this system on the quick. that make sense? All right, so getting towards the end of this stuff here, but hang with me. How nasty can it get? Well, wait, okay. You'll enjoy this. Here we go. Another definition. And the definition is this. The adjunct or adjoint of a matrix. So this is the definition. And the adjunct, I'll have to admit to you, I don't use that term that much, even on my linear algebra classes. This is just a fancy word for it. We typically know it as the adjoint, okay? The adjoint of a matrix, and most math professors will call it this, the adjoint of a matrix. The adjoint of a matrix is this, and we have symbols for everything because we can't spell. ADJ is adjoint of matrix A is equal to C11, C12, C13, C1n, all the way down, Cn1, Cnn, transpose, which is a matrix of cofactors. Uh-oh, using a term that I did last time. What is a cofactor? Okay? Now, where the Cij is the cofactor of the ith row and the jth column of a matrix. Okay? And before I talk about this, let's talk about it for a second. So, come over here just to talk about it. So, I'm going to do a matrix for you guys, and I'm going to do it 3 by 3. Now, I can make it, I can make this A11, A12 thing here, and that will probably confuse half of you guys following the numbers here. So I'm going to make it simple. So this is what we call the quote, cofactor, okay? So here it is. I'm going to make it 3 by 3. It is let's see here, A, B, C, D, E, F, H, I, I guess I left off the G, but who cares? Okay. A, B, C, D, E, F, H, I, J. Just, there it is. There's my letters. Just trying to represent a matrix here. All right. Now, what would the C11 be? Well, the thing you're going to put beside it is the sign matrix. You remember us talking about the sign matrix? This guy is 3 by 3. So this is plus, minus, plus, minus, plus, minus, plus, minus, plus. If we did 4 by 4, you would expand it, 5 by 5, so forth. This was the sign matrix here. All right. So, for C11, this is your first row, first column position. So, focus on that guy and knock off the row and column with it. Does that make sense? All right. And so, the C11 would be the determinant of the minor matrix. E, F, I, J, and you got to take the sign with it. Make them positive. Plus whatever that number is. Does that make sense? Okay? What about the C12 guy? Who's he going to be? Well, that's going to be the C, first row, second column. That's the B guy right there. So you focus on him next. You knock off the row and column with that, and you get the minor matrix, which is going to be D, F, H, J, and again, you see the little lines there, parallel lines? You're going to take the determinant of that. So DJ minus F, H. Does that make sense? But the sign is this guy is going to have to be negative. So whatever number you get here, change the sign up. So far, so good? Let's do one more here. C13, who is that going to be? That's going to be that's where the C is located at, right? Knock off the row and column with the C, and you get the D, E, H, I, and you take the sign, so we're back to plus again, and you take the determinant of that guy, and that's going to be that entry right there. Well, let's do all of them. This will be C21, which would be, knock off this guy here, the row and column with it, and you're left with BC, IJ. What the sign is, take the negative. Then you got C22, that'll be the guy in the middle. So knock off the row and column with the guy in the middle right there, and you get ACHJ, ACHJ. And this is going to be a plus. And then you got C23. So C23 position, the second row, third column, knock off that particular position, row and columns. You get ABHI, ABHI, but that's going to be a negative, so the sign goes with these guys. That's where most people forget is the signs on it. And then one more row here, you got the C31 position. And so that's the H position there. So you knock off the row and column with that. You see the minor matrix BCEF, BCEF, and the sign on that one is back to plus. The C32 position, you're going to take the determinant of that's position here, so knock off the row and column with that. And that's your ACDF. Okay, and that one is negative. And then one more, C33. Okay, what is your C33? That's the third row, third column position. So you got that guy right there, and you got ABDE, 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 and that sign is going to be positive. Does that make sense? So the adjoint matrix is going to be the matrix that has these numbers. Remember, these guys are going to be numbers when you take the determinant of it. They're numerical values. So it's going to be the C11, C12, C13, C21, C22, C23, C31, C32, C33. And to make the adjoint, and this would be the adjoint of the original A matrix, we would call this guy A up here. So, but the only other thing you got to do is transpose it. Rows become columns, columns become rows. Does that make sense? Again, why do you care? Because we tell you to. But no, more important than that, there's a reason why you want to do this. It is this. The last little bit. And that is A inverse is actually equal to 1 over the determinant times the adjoint of A. So when I get that adjoint of A matrix, you've got to multiply by 1 over whatever the determinant of that matrix is, and that will actually be another way you can find the inverse. So these determinants, even though they're kind of weird in terms of creating these numerical values that kind of rank the matrix, they are used to actually manipulate matrices. We can actually find inverse of matrices just focusing on the determinant of certain aspects of your matrix. That's what's going on here. So, the only way to truly learn this stuff is do an exam. Again, 2 by 2 inverse is easier to do that. So the most I'm ever going to do is going to be 3 by 3. I have seen 4 by 4s done. It doesn't matter. They got to be square. But fact is, again, for efficiency, I'm afraid, smaller is going to be 3 by 3, 4 by 4 is the most we'll ever do on this one. So I want you to find the inverse if A is equal to 3, 6, 7, 0, 2, 1, 2, 3, 4. All right. So here we go. Now, first thing I'm going to do is I'm going to find the cofactors. So we need to find the cofactors. Well, remember, when I draw out one of these matrices, right beside it, I'm just going to remind myself, because that's where most people mess it up at, they'll forget to actually also throw the signs in there. So again, this is 3 by 3, so it is plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay? So, what is C11? What would that be? First row, first column, knock it out, 2, 1, 3, 4. 2, 1, 3, 4, and it has a sign plus. All right, okay, I'm going to not write out everything for you guys. We can take determinant. 2 times 4 is 8, minus 1 times 3 is 3, 8 minus 3 is 5, and it's plus 5. Find C12. What would C12 be? C12 is where the 6 is at. Knock off the row and column of that guy, and you get the 0, 1, 2, 4. 0, 1, 2, 4. However, what's the sign of this guy? It's negative, so I'll get the negative out front. So this would be negative, here we go. 0 times 4 is 0, minus 1 times 2 is 2. 0 minus 2 is negative 2, which makes the answer 2. Does that make sense? Keep going. C13 would be first row, third column, knock it off. 0, 2, 2, 3. 0, 2, 2, 3. And that sign is going to be back to positive. So that would be 0 times 3 is 3 minus, 0 times 3 is 0, minus 2 times 2 is 4. 0 minus 4 is negative 4, and you keep the sign of that one, so that's negative 4. C21. And you'll notice this thing, I could speed this process up, but I've found in teaching this class many times before, that tends to frustrate students to no end because they're trying to keep up with me. And as I talk, you should continue to write this mess down. So I'm trying to slow up so you guys can keep up with this stuff, because I could speed up and just completely lose you. I don't want to lose you. It's not difficult, it's just tedious. 2, 1. So second row, first column is where the 0 is at. So if I knock that part off, I got 6, 7, 3, 4. 6, 7, 3, 4. And that sign is going to be negative. So that's negative 24 minus 21. What's 24 minus 21? 3. But the sign goes with negative 3. Does that make sense? All right. C22. C22 is this where the 2 is at. Knock off the row and column with it. 3, 7, 2, 4. 3, 7, 2, 4. And that's your middle term there, so that's going to be plus. So that's 12 minus 14. 12 minus 14 is negative 2. C3. Question. C13. Nope. Let's see here. Main diagonal. 0 times 3. 0. Minus 2 times 2. 0 minus 4. That's negative 4. And it's a plus on that one, so there's no sign change. So C23. All right. Second row, third column. That's where the 1's at. So knock off the row and column. I get 3, 6, 2, 3. 3, 6, 2, 3. And that's back to a negative on that one. And that's going to be 9 minus 12. Negative 9 minus 12 is what? Negative 3. And the negative 3 is 3. Does that make sense? All right, keep going. C31. 3, 1 is this position right here. Knock off the row and column with that in it. 6, 7, 2, 1. 6, 7, 2, 1. And that's going to be a plus on that one. So that's 6 minus 14. 6 minus 14 is what? Negative 8. And keep the same sign there. C32. Third row, second column, knock off the row and column with that in it. 3, 7, 0, 1. 3, 7, 0, 1, but that's going to be a negative there. And that's 3 times 1 minus 7 times 0. 3 minus 0 is a 3. Negative that makes it a negative 3. And one more. C33. C33 would be third row, third column. Not that would be the 4 is that. You get 3, 6, 0, 2. 3, 6, 0, 2, and that's a plus on that guy. So that's 6 minus 0, which is 6, positive 6. I pretty much get 6 there. Okay? All right, so remember, A inverse is equal to 1 over the determinant of A times the adjoint of A. So this is 1 over the determinant of A times, what is the adjoint of A? It is these numbers here. Well, I'll do this. C11, C12, C13, C21, C22, C23, C31, C32, C33, what? Transpose. So now we're going to put the pieces of my puzzle together. So this is 1 over the determinant of A. We'll get that in a second. Let's go ahead and do this guy. C11, what was this? 5, next one is 2, next one is -4. C21 is -3, then -2, then 3, and then -8, -3, and 6. But don't forget, transpose. All right, wait a minute, not done yet. I still got to find the determinant of A. Would you guys mind helping me figure out what the determinant of A is? All right, so remember how to take a determinant. Since we're doing all these cofactors, wouldn't it be more advantageous if we did the expansion by minors? Because these cofactors are the minors. Does that make sense? So pick a row and or a column, your choice here. I'm going to pick the top row. Why? Because it's the top row. Here's the top row right here. All right. And so the determinant of A, if I do this guy, that is 3. I'm going to use 3. And then I'm going to use my the sign of this guy down here, because you knock off the row and column. What was that cofactor there? It was what? C11. Just want you to see this. It's C11. Okay? And then it becomes, the next one's going to be plus 6 times the cofactor of this guy, right? And that was the cofactor, that was going to be C12. I'm writing this down here. I'm going to minimize this a little bit so you can see this. All right? And then it's plus 7 times C, knock off the row and column, and this is the matrix of C13, the 0, 2, 2, 3. Does that make sense? Well, wait a minute. Don't you need to put the signs in it? No, I don't. You know why I do not need to put the signs in it? Because the signs have already been put into the C11, C12. So it's just figure out a row or a column that you want, and then use the minor matrix off that. And these cofactors already have the signs from the sign chart already embedded in them. So this would be 3 times, what was C11? C11 was 5. Plus 6 times, what was C12? That was 2. Plus 7 times, what was C13? It was -4. Let's calculate that out. That is 15 plus 12 minus 28, right? 7 times 4 is 28. So, help me out here. What is 15 plus 12? 27. Minus 28. -1. I got the determinant of A. Using those cofactors, since I've already done it, I can use them to help me figure out the determinant of the actual matrix. So therefore, A inverse will be equal to 1 over the determinant of A, which is -1, times the adjoint matrix, which is 5, 2, -4, -3, -2, 3, -8, -3, 6, transpose. All right. 1 divided by -1 is -1. I'm going to take a negative and basically put it through every term in this matrix. So I'll just do it in steps here because I'm afraid I'll lose you guys. That'll be -5, -2, +4, 3, 2, -3, 8, 3, -6. The last thing I got to do is transpose it. What is it when we transpose a matrix? What do? They'll make the rows and turn them into columns. So the first row becomes the first column. -5, -2, 4. The second row becomes the second column, 3, 2, negative 3, and the third row becomes the third column, 8, 3, negative 6. Bum, 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 bum. Therefore, with the whole page of it, that A n should equal to negative 5, 3, 8, negative 2, 2, 3, 4, negative 3, negative 6. Does that make sense? Using adjoints. But with that being said, is this efficient? No. How can I check my answer to make sure I didn't screw it up? How did we do inverses before? Okay, so look, it took me a whole page to do this thing, but all I was doing is basic numbers, putting them in there, and I tried not to skip any steps. So I went slow. I could speed this process up greatly if I needed to. But if I was going to do this, or better yet, if you were going to do this on my test, okay, here's matrix A. And I end up getting, and gave you matrix A, 3, 6, 7, 0, 2, 1, 2, 3, 4. And I tell you guys to find A inverse. How do you guys, what were you trained to do to find A inverse? Outstanding. Augment with the identity. A, augment with the identity, which would give you 3, 6, 7, 0, 2, 1, 2, 3, 4. Augment with 1, 0, 0, 0, 1, 0, 0, 0, 1. And then, what are you going to do? Our goal here is to reduce row echelon form this guy, which will give you 1, 0, 0, 0, 1, 0, 0, 0, 1. And it would be augmented with the inverse guy. Does that make sense? Now, how would you do this problem? Again, it's this efficiency aspect. See, in the past, I have been very, very nice to you people. I've always put a 1 relatively close by that first row, first column position to make it something nice to help you out with the reduced row echelon form. What you going to do on this one? What's your first move? That's what I'm asking. If you were going to do reduced row echelon form on this matrix A, augment with the identity, what are you going to do? You need to make that 3 into a 1, right? What you going to do? Divide by 3, right, by the first row. I mean, I can't really row swap anybody. That's a 2. So I could row swap this guy, but then I have to divide that row by 2. So I don't care what you do. You're going to get a 1, right? You're going to get a 2, right? And you're going to get a 7/3, okay? And you're going to get a 1/3. You can't avoid fractions on this thing. That's my point. And with the fractions, man, you think it's slow going and trying to reduce row echelon form. I've been nice to you guys. I've tried to give you problems that the fractions show up kind of at the end. This one, you can't escape it. The fractions will be right at the beginning, which means in terms of the time, I mean, I'm talking about your time, not talking about computers. Your time to actually find the inverse of this guy has now gone down to a snail's pace of you guys having to manipulate fractions throughout this guy. So in that sense, you know, this now becomes a lot more efficient when you look at that particular aspect of it, okay? So just something to the note, but honestly, for most of them that I give you that you can get a pivot right up here, you'll sweep down. You still maybe get fractions, but you know, if the fractions are at the beginning, it does slow you down kind of considerably. But this is how we would do it in the quote-unquote old days of chapter 2 at the beginning, which is, again, what your test is going to be on. So just a little side note on that one. All right, let's keep moving. Why? Because we can. One last thing, definition. What else can we do with this awesome material dealing with determinants? Now, this is something that you typically would use in a Calculus 3 course, for those people that stuff. And it is this. All right? To calculate the volume is equal to the determinant of A, which is the volume of the parallel pipe determined by the columns of A. All right. And in 2 dimension, instead of being volume, it will end up being area. All right. So let me just describe for you guys what's going on here. So I need a nice clean sheet of paper just to set it up. In 3D, and again, I'm just going to draw this kind of arbitrarily here. 3D. Welcome back to Calculus 3 for those who have had it. Not a prerequisite for the course, but if you're in this class, you'll probably end up taking it sometime. So here's my 3-dimensional XYZ plane. All right. You guys know what a parallel pipe is? It's a parallelogram in 3D. So you get this idea that this thing has been kind of shifted over here. So it'd be kind of tough for me to draw, but you know what? I'm going to try to draw this thing. So you'll have this kind of a rectangle looking thing up here. Okay. And let's see here. I kind of wanted to draw it. This way. Okay. And then you've got this. Okay, it's minor drawing, so give me a break on my awesome art ability. And we connect these guys. Okay. Imagine these guys being parallel. All right, so what does this look like? Looks like something that my son helped me with to build one of his shelves. Okay, so we got a problem here. We were building shelves and man, I didn't make it vertical, did I? Darn thing shifted on me. So this is the parallel pipe type thing here. Now, you got vertices here. You got a vertice here, 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 and here. So this is what we call a parallel pipe. It is a box that's kind of skewed. That's the fancy word for a parallel pipe. A box that is skewed. Your job is to find what the volume is. Now, if it was a regular box, that wouldn't be a problem. It's length times width times height. My problem is it shifted on me. Okay? So, how do I do this? Now, each one, this is a 3D point type thing here, so I'm just going to put like numbers down here. A, B, C, D, F, G, I, J, K, L, N, O, P, Q, R, S, T, U, okay, I missed one point here, Q, that's a U there, this is a V, W, X. Okay, so I got points all over the place. You with me? Now, what you need to do is you need to create the 3 vectors that actually make up this box. So, I'm going to pick a point that I like. I like this point down here at the bottom. I'm going to call him point A. Okay? And I need 3 other points, because remember, this is parallel. So, this line is parallel to this line, parallel to this line, parallel to this line. This line is parallel to this line, even though it doesn't look like it. Parallel to this guy, parallel to this guy. So I need 3 points. So I focus on one point, and I see who's connected to it. I need this point here, B, okay? I need this point here, C, okay? And I need one other vector, all right? So to create this guy here, to get this parallel pipe here, I need this point, A, B, C, I'm going to call this point D. With me? Now, you need vectors. I want this vector right here. See, because you're going to create the 3 lines that are parallel. This line is parallel to this line, which is actually parallel to this line, parallel to this line. Okay? So, how do I create the vector A, B? Again, this is calculus 3 at its best. End minus beginning. You're going from A to B. To calculate the vector, you do B minus A. And these are components. You're going to create the vector okay? I see D minus A, comma, E minus B, comma, F minus C. That creates one vector, okay? I'm focusing on this base point A, so you only want to have a fixed point that you're focused on. The next point is going to be the vector, let's go A to C. How do you get AC? N minus beginning. This was S minus A, T minus B, and U minus C, okay? And then you get the third point, this third vector over here, which is AD. And notice what you got is parallel line, parallel line, parallel line. There, see, in a parallel pipe, there are three parallel lines. You're either parallel to this guy, parallel to this guy, this one's parallel to this one, parallel to this one, you're parallel to this guy. So there's always, you've got duplicates of these parallel lines. Does that make sense? And you need one of each one. So AD, N minus beginning. So D minus, that'll be V minus A for the first component, W minus B for the second component, and X minus C for the third component. Okay? Now, according to my theorem, to calculate, we're going to create a matrix of all these guys. So you're going to create this matrix by putting this information in columns. So this would be the AB vector in column. This would be the AC vector in a column. This would be the AD vector in a column. You with me? So these will be numerical values. So this is what? D minus A, E minus B, and F minus C. This one right here would be S minus A, T minus B, and U minus C. And this one would be V minus A, W minus B, and X minus C. And you got yourself a matrix, right? A determinant of matrix A, absolute value, because the determinant could be negative, but the absolute value of that would be the volume of the parallel pipe, which is the structure here. That is the idea. And the Calc 3 is how you create a vector in Calc 3, N minus beginning, classic chapter 9 in your calculus textbook when you do Calc 3. N minus beginning is how you create the vector. Well, that's a wee bit of a pain, so, but wanted to show you the idea of it in case you happen to have one on your homework set in hand. However, I did an example in 2D. In 2 dimensions, a little nicer, and it's easier to draw, okay? So, in 2 dimensions, this is what we got. In 2D, it's 2-dimensional, so instead of volume, it'll be area, but you get the exact same thing. So, it says, but in 2D, it's called a parallelogram. A parallelogram, a 3-dimensional parallelogram is called a parallel pipe. Just give you the connection here. So, find the area of the parallelogram determined by the points, vertices, of 0, -2, 6, -1, -3, 1, 3, 2. So the first thing I would do is draw this guy out. Get a feel for it. And you got some negative numbers here, so let's have to go into your other quadrants here. X, Y, 0, -2, -1, -2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. I think I got enough there. All right, here we go. So let's graph this guy. 0, -2. That's down here. In case you can't read where my dots are at. 6, -1. 1, 2, 3, 4, 5, 6. -1. Right here, this is the point. 6, -1. -3, 1. 1, 2, 3, -3, 1. That will be up here. And again, labeling them as -3, 1. And then one more point is 3, 2. 1, 2, 3, 1, 2. It's up here. Okay. 3, 2. And I'm going to label these points just to make it a little bit nicer for me. I'll call this guy A, B, C, and D right there, just to kind of go counterclockwise with them. And if you connect the dots, you will see the parallelogram. There's my parallelogram. Does that make sense? And so as I look at your papers and looking at your awesome drawings, and for the people that do it on their iPads or whatever, okay, but whatever, piece of paper, pencil, whatever I can see. Hey, this is sad. Okay, but how did I make mine look better than yours? I look better than I'm an artist. Okay, fine. But you know the trick of the trade. My hash marks are really close to evenly spaced. Okay, there's me going a little bit off on it, but they're evenly spaced. If you look at your hash marks, you just chunk down some hash marks, and some are a little bit closer than others. You get all kinds of interesting shaped pictures when you do that. Again, remember that neatness counts thing? You'll learn later on that it's helpful to be neat and stuff. All right, so how do I find the volume? Well, with a parallelogram, you need two lines that are parallel. With parallel pipe, there were 3 lines that are parallel when you do the 3D. This one, there's 2 lines that are parallel. So pick a base point. I like A down here in the corner, especially because it's got a 0 on it. So I'm going to pick this vector here. There's one line that's parallel. And I'm going to pick this vector here. So I've got to create a vector, A, B vector. And I'm going to pick the A, D vector. So I'm starting at A, going to B, and I'm starting A, going to D. Remember the rule. To create a vector with points, you do end minus beginning. It gives you that direction into it. The direction, honestly, is not going to matter because the determinant is going to be the absolute value, but the directions, we'll put a sign on this stuff. So these will be vectors, and I'll use my pointy bracket for vectors here. End minus beginning. So this would be, and I'm going to write it out here so you guys don't mess it up, A to B, so it's B minus A. First component is the x component, 6 minus 0, comma, negative 1 minus negative 2. And I wrote it like that for your benefit because it's real easy to make a bonehead careless error with this stuff. So I end up getting the vector 6, comma, minus 2 is plus 2, negative 1 plus 2 is 1. So that's your vector there. Now the AD vector, end minus beginning, negative 3 minus 0, comma, 1 minus negative 2. This would give you the vector negative 3, comma, 1 minus negative 2. 1 plus 2 is 3. I get the vector negative 3, 3. So the matrix A is going to be the matrix putting these vectors in the columns. This would be 6, 1, and negative 3, 3. Putting the vectors as column vectors. Does that make sense? And now, watch this. The determinant of A would be 6 times 3 minus negative 3 times 1, which is 18 plus 3 when you clean it up. And what do I end up getting? 21. And officially it's the absolute value. This one, because the numbers worked out well for me. Absolute value. And the absolute value of 21 is 21. So 21 squared units is what the area of this parallelogram is. Does that make sense? And again, you do the same thing with volume, but it's 3 dimensions. So you got to get 3 of those, three lines make the parallel pipe. 2 lines make the parallelogram with the lines that are being parallel. So that's how you do it. Does that make sense? Again, another interesting aspect of determinants that show themselves in Calculus 3, if you look at Calculus 3 the right way. Okay? So, and again, in terms of these interesting formulas and the like, we have this in terms of volume of TS. If T goes from R2 to R2 is a linear transformation, and S is a parallelogram, okay, then the area of TS is equal to the absolute value of the determinant A, which is the area of S. So this matrix A, when you actually put in these column vectors, you're creating that linear transformation that when I take the determinant of it, it'll actually give me what the, quote, area of the parallelogram is. And similarly, if T goes from R3 to R3, and you have that linear transformation, and you're creating it with that matrix A when you set up these vectors here. S is a parallel pipe, that's your three-dimensional parallelogram in R3 here, then the volume of the parallel pipe in that S3 will be the determinant of that linear transformation T matrix, which is A, and it gives you the volume of that parallel pipe. That's exactly what's going on, and you can see with these matrices that we were creating, these are actually your linear transformations. And this was the linear transformation that's converting this stuff over. So there's a nice tie-in to all this beautiful stuff. But again, chapter 3 is about what can we do with determinants. Because most people, when they first see determinants, they look at it and go, this is just manipulating numbers off of a matrix. What can that do for me? Believe it or not, quite a bit. Does that make sense? All right, that's the end of chapter 3. Yay. So what do we do then? Go to chapter 4, of course. So, chapter 4 is on vector spaces, okay? Oh, no. So chapter 4 is on vector spaces. And so, of course, there is big definition. And we're going to talk about the idea of a vector space. So again, introduction to linear algebra, big definitions here. Now, we've already talked about spaces before. We talked about the definition of a space, or more likely a subspace. And we talked about how to create a subspace, which is the basically the linear transformations, okay, or the linear combination, excuse me, the linear combinations of all the vectors within what we call a basis. And so we talked a lot about bases, spans, and all this other stuff of vectors creating these spaces. Now we're going to look at vector spaces as a whole, as a component to study. And so it's going to tie back into all that stuff we did in chapter 2, okay, with this idea of, we had column spaces, row spaces, null spaces. These are particular examples of spaces. We're going to look at spaces in general. Vector space. A non-empty set V of objects called vectors on which there are two operations, an addition operation and a scalar multiplication, which must hold to the axioms below. These must hold to or be true for all vectors, U, V, W. You see the little lines I put above it? These mean these are the vectors in your, quote, space V. And for all scalars, C and D. So C and D don't have little lines on them, so this is how you can distinguish between when I'm talking about a vector and when I'm talking about a constant, a scalar. So, this is the properties or axioms of a vector space. Number 1, sum of two vectors. If you got U and V in this vector space V, then vector U plus vector V must be in the space V. This is called closure under addition. We have closure property. If I got a couple of vectors that got to be the same size, they got to come from the same space, R3. They're three-dimensional, so you can actually manipulate these guys. So you take one vector from R3, add another vector R3, it's got to be back into a vector in R3, okay? But we're going to be talking in general, so we're not always going to be talking about R1, R2, R3, R4, or whatever. That's our standby, and that's what creates these matrices. But I can also talk about other spaces as well. Why do we have to have R? Why can't we have a complex number? Why can't we have integers or something like that? What's going to be a space and what's not going to be a space is what we're talking about here. So the first thing you've got to make sure is you've got closure. If I take two vectors inside my set, the sum of those two vectors must be inside my set. Commutativity under addition. It should not matter what order you add the vectors in. U vector plus V vector is going to be the same thing as V vector plus U vector. Again, I'm going to be switching up where the components come from. So you never know what kind of system I'm going to set up for you guys. But whatever system I set up, when you take vector U plus vector V, that's got to be equal to vector V plus vector U. It's called commutative under addition. Also, if I got three vectors, U, V, and W, if I take vector U plus vector V, add those together, and then add the W, and then add vector U plus vector V plus vector W, add the vector V and plus vector W together, order doesn't matter. Notice the parentheses. So when I'm moving parentheses around, what's the fancy word for that? Associativity. Commutativity, you can move elements around. Associativity, you can move parentheses around. Under addition, it works. Any kind of vector space, you've got to have a zero vector in there. We kind of played around with those linear transformation type ideas. The zeros have to map to zeros. The zero vectors has to be inside your space. So there's got to exist a zero vector inside your space. And what's the property of zero? Any vector u plus the zero vector will be equal to the zero vector plus vector u, and you're just going to get back vector u for all vector u's in your space V. Any kind of vector you have to have the additive identity. The additive identity, or additive inverse, if you will. Okay? Excuse me, this is the additive inverse here. For any vector u inside your space, there's going to exist a negative u inside your space, such that u plus negative u is equal to negative u plus u, which gives you back the zero vector. So if you think about a negative vector, it's a vector that basically you change direction to. Remember that n minus beginning? That's going pointing out from A, D, you're going D minus A. It points from A to D. If I want to point from D to A, all I can do is make it negative. And that just change all the coefficients, all the terms, and it just changes the directions. But when you take u and add it to the negative u, it should completely cancel out, and you're back to having that zero vector that has to be in your space. That's called the additive inverse vector. In terms of scalars, if you got a vector v inside your space, and any scalar c that comes from the world that you're manipulating constants with, you take a scalar times a vector, that should be also back inside your space. Any scalar times any of the vectors inside of v, their product has to be inside of v. Scaling it. So, if I got a vector that's 1 unit long, I multiply it by 2, it's now going to be 2 units long. I can multiply it by -3, that'll be 3 units long going in the other direction. This is any scalar will actually also put the vector inside your set. Now we have two different types of properties of distribution. You can distribute by a vector. So if you've got two scalars, c plus d times vector u, you can distribute the u, and that's equal to cu plus du. That will always work for a vector space. And you add a couple of scalars together times a vector, you can distribute the vector throughout. Or you can distribute the scalar. Scalar c times vector u plus v is equal to the same as c, scalar c times vector u, plus scalar c times vector c, times vector v. This is called, distributing the vector is number 7, distributing the scalar is formula number 8. And if you're multiplying a couple of scalars, again, you got associativity. It doesn't matter what order you multiply these guys out. C times du is equal to c times d times u, okay? And you can either multiply the du times u and then multiply the c, or multiply the c times d and then multiply it by u. That doesn't matter, it'll work. And then the last one is, there's something called a scalar identity. The scalar identity is one that's real obvious, but it must happen. If there's there's got to be a 1 inside your set of scalars, that when I multiply it times my vector, I'm just going to get the vector back again. That's your 10 property that actually tells you that you actually have a vector space. Now, here's the problem with that, okay? The problem with this is, man, these 10 things are awfully tough to prove. If I actually prove this is a vector space, man, you got to show me 10 things whole. That's tough. So to shorten it up, we're going to be looking at not just vector spaces, but vector subspaces. We give you an overriding vector space, which you've already proved, like an R3 or something or other, and then talk about a subset within R3, and I'll make you prove that's going to be a subspace. There'll be less properties on that. But the last thing before I let you guys go is this. So just some interesting results. All right? From that property sets. The zero vector is unique in any kind of vector space. 0, 0, 0, or however many components you got, it's going to be your zero vector. The 1 is unique in terms of your scalar. There's only going to be one 1 that you have. You don't have different kinds of 1s or something like that. Okay? For any vector u inside of v, the negative u is going to be unique inside of v. And 0 times a vector, it gives you the zero vector. A scalar times a zero vector is going to give you the zero vector. Negative vector u is the same thing as -1 times u. just to let you know the relationship, because 1 is in there, that also means that -1 is going to be a scalar. And just some basic examples of some vector spaces that you should already know. But some of you don't know. So I want you to look at this real quick before I let you guys go. You're familiar with Rn. Rn, R3, R4, we've been beating that since day one. That's a vector set for any n greater than or equal to 1. V, here's one, the set of all arrows in 3D space. So not only do we talk about numbers, we can talk about symbols. You know, the arrows, where 2 arrows are considered equal if they have the same length and point in the same direction. Here's another one, so you get this visual aspect of vector spaces. Here's another one, Pn, where n's greater than or equal to 0, P is the set of polynomials, you know, 3x squared plus 2x minus 5 type thing here. You can look at the set of polynomials. P of t is equal to P naught plus, A naught plus A1t plus A2t squared plus plus AN t to the n. This is a polynomial where the A1, A0, A1, A2 are the coefficients, and your polynomials in terms of t is the variable. You notice that the degree of P of t equals 0 if and only if P of t is equal to a constant. Okay, and here's the deal, A0 can't be equal to 0 for the degree of 0. Here's another one, the set of all real value functions. I can look at functions. Function plus a function is another function. I can multiply them by scalars, I can add 2 functions together and get another function. That's going to create a vector space. If you look at those 10 properties and multiply by constants, you're still going to get those 10 properties. As long as I can get those 10 properties out of something or other, I have a vector space. So vector spaces are just more than just your classic Rn. You can look at them with other different concepts, and that's what we'll look at. Study hard, and I'll see you guys on Tuesday, where we'll continue on with chapter 4. Don't forget your homework. Number 4 is due on Thursday. See you guys then.